Welcome you all to the session 2. We have a expert lecture by Asish Kumar Sengupta, MD, Deltasun Technoventure LLP. Before beginning the session formally, I would like to introduce our honorable speaker. Asish Kumar Sengupta began his career in 1976 as an assistant project engineer at Crompton Greaves, managing significant projects such as Indian Telephone Industries, IFFCO, Phulpur, and Switchyard in Sultanpur. He founded Delta Power and Engineering Corporation, gaining a strong reputation for designing and manufacturing power and distribution, transformer, and various electrical panels. In 2020, the company transitioned into Deltasun Technoventure LLP, where Mr. Sengupta now serves as the managing partner and CEO. Now, I request A.K. Sengupta sir to enlighten us. Sir, please.
So let us start with what is power factor. So normally we know the power factor is the ratio of a real power which is used by the system to the apparent power and supplied to the system, and which can be expressed. We know that P by S unit is cos phi, where phi is the phase angle between the voltage and current. Okay. Now, what is that important thing about the power factor control? So in the present situations, the evolutions of growing in computers, laptops, and uninterrupted power supplies, telecom biomedical equipment has become overpowering. Hence, the utilizations of such equipment results high power consumptions and small power density, which provide a large market to the distributed power systems. So power conditioning, typically rectification, is essential for usually for electronics equipment. Rectifier behaves as a nonlinear load, producing non-sinusoidal line current due to the nonlinear impact characteristics. The steady growth of the use of this electronics equipment is become significant problem as per the limit the harmonic is concerned, and their adverse effect on the power systems are acknowledged healthy. So that's what suppose a three-phase systems, the neutral current magnitude increase and becomes the cause of overheating of transformers and induction motors, as well as the dreadful conditions of the system voltage waveforms. So there are numbers of international standards where we can see a reduction of the line current harmonics or a power factor corrections is very essential, and that this power factor control is vital. And this idea is the inspirations of this research topic, and the objective is to improve the power factor nearly unity with minimum total harmonic distortions. So we know, so there are two type of power factor controller. This is passive power factor controller and active power factor controller. And for this type of these upcoming lectures, so we will try to see a small EMI LC passive power factor controller and boost converter active power factor controller, which will be presented with the suitable switching control. And we know that different conventional and nonlinear control schemes are analyzed for the switching of boost power factor converter. So let us start with the two major conventional control techniques that are to be implemented for this upcoming this lecture, where we can show that peak current control and average current control and PI control. And also we'll try to see that dynamic response and large stability range of high frequency nonlinear controllers like a dynamic evolutions controller and sliding mode controller, which are applied. And for each cases, we'll try to see that input power, which is very close to unity, and the line current waveforms is observed with a sinusoidal with total harmonic distortion, which will be present, which will be in the percentage in this tolerance limit. So we can see these basic things of we have just go through, and so this slide presents a very simple slide presentations where we can see the power factor, which is nothing but the ratio of real power by apparent power. And our aim is try to fix this power factor, try to very near to unity. Okay, and so this is very simple slide where we can understand the normal what is the power factor. Now we'll try to deal with this power factor, how it is in front of the power factor controller in case of electric vehicle systems. So this is the formula. This is also shown for the total harmonic distances, where you can see that total harmonic distances formula is written here.
Slides are not moving.
It's not
Slides
moving.
are not changing.
It's changing.
No,
So
sir.
it's changing.
No,
It's
no,
not
sir.
changing.
Yes, now it's changing.
It's changing. I'm extremely sorry because I'm sitting in a remote area. No, so
Okay,
that's
okay.
the problem, sir. It's showing now, sir.
Yes, sir. Yes, sir. It's showing.
Oh, okay,
Now
sir.
it's
Okay,
showing.
sir. Okay. So this slide, we have shown this total harmonic distance distortions, where we have seen the these formulas, and where the basic block diagrams are also given, and that power factor correction. So normally it is a measurement of the degree of the utilizations of the power from the grid, and mathematically we can say it is the proportions of the real power to the apparent power, and the range is power factor is 0 to 1. So normally the real power, which is measured in watt, and the power necessary for real work done, and apparent power is nothing but it is in volt ampere, and it is the vector summations of the active and reactive power. For a pure sinusoidal voltage, so power factor is nothing but it's cos phi, where cos phi is the displacement factor for the voltage and current. And in general, power factor controller tends to be the compensation of the displacement and factor. And but for the nonlinear load, so what will happen? So for a sinusoidal line voltage and non-sinusoidal line current, waveform of power factor can be expressed like Vrms Irms upon Vrms Irms into cos phi, or also we can write Irms by I1 RMS by RMS in cos phi, or directly we can write down this what you call the Kp into cos phi. So in this Kp is nothing but I1 RMS and by IRMS, and which is a subset of 0 and 1. And these formulas, the formula which is written in this cursor, so it is in that we derive that total harmonic distortions is nothing but those formula, and Kp is nothing but 1 by under root of total harmonic distortions. So this power factor is nothing but here's Kp, and therefore like with a substational harmonic current which is achieving of high power factor can be possible. How is it possible? The power factor is not much affected by the harmonics unless their amplitude is quite large, like a low Kp and very large total harmonic distortions. Also, like a small harmonics content does not assure high power factor, and this Kp value, no, it is very close to unity, but low power factor cos phi. So in simple words, we can say the power factor correction is referred as the minimizations of the line current harmonic, and the main objective of this what you call this presentation is nothing but the power factor corrections, which is maintaining a least phase angle between the input voltage and current with the improved total harmonic distortions level. That is like keeping the harmonic content to a minimum level, and the effect of harmonics and its problems on power systems is observed as significant, and hence electricity regulatory commissions and utilities all over the world is penalizing the users for harmonic dumping into the supply lines. And Central Electricity Regulatory Commissions of India has given a guideline to institute electrical and electronics engineers standard 51992 on permissible limits for harmonics in the electrical systems, and both the utility and users should know like the understand of standard and essential time and specified. Now as we discuss about this power factor, about voltage distortions, now we can see these particular slides where we have shown what is the benefits of the high power R factor. So this voltage distortion is less, and all the power is active, and small RMS current, and higher number of loads that can be fed. Okay, and these are the advantage where the circuits with the power factor controller is also describes where you can see the cost saving factor, like the electrical loads, SMPS, electronic blast in unit or other electrical load become much simpler. So similarly, the second one, the problem also, the advantage we shows for power factor controller, where we have seen the smaller RMS current with a power factor controller, it permits to use a very small and much cost-effective means rectifiers to the manufacturer of electrical load. And this third one, you can see where the input voltage for the DC electrical load becomes stable and regulated, where AC to DC systems because operates on wide range power supply for the power factors. And if you know, for earlier discussions, what we have done for the nonlinear loads and the distribution network, the line current harmonics introduced, which need to be minimized. So that has to be keep in mind while doing this modeling. So there are the number of procedures which shows the power factor corrections, though there are so many research papers already has been discussed, but mainly it can be categorized into methods like a passive method or active method. In LC filter, what we can use for the passive power factor controller approach, or here if you move those particular things. So for here directly we can see these are the advantage for the boost power factor controller, where it can attain a very low of the total harmonic distortions and offer a possibility the best power factor and higher output voltage. Also we also used to get it here, where in terms of the size and efficient energy storage capacitors, and for switching current sense and the grid drive because of low side boost switch. And these one more advantage we consider relaxed for and those though we're using for boost power factor control performance, but this and now suppose this and like at a startup, since there is no ingress limitation, a costly ingress limiting mechanisms with a highly disadvantage characteristics is required, and there is a significant drop in efficiency at a low line due to the higher difference between the AC input and the bus voltages. And these advantages also, like it is easy functionalness, safety, spacing, isolations, and regulating stage, and across power factor stroke, there is a small difference in input to output voltage, hence merit to use a smaller value of inductor comparatively, and easy of control, and no need to AC line sense reference and multiplier to obtain the total good total harmonic distortions and power factor management. And auxiliaries mechanisms for risk current is not required, and based on this free. And this now how you like going to motivate this your for bus book motivation is nothing but here like the most electronic equipment like at the distinct power rating, and hence like amazing demands of the power source for such equipment like tens and great task to the power engineers. AC to DC and active power factor converter systems introduce the idea of regulated DC bus power voltage on power distribution and management. This fulfills the higher current desires and dynamic characteristics of AC to DC systems for specific applications like power source to the telecom industries and computer services, biomedical equipment, and aeronautical engineering. It is too humbling while considering high efficiency, high power density, and fast dynamic response. What will happen? The transfer for electrical power from grid to consumer end is possible with low cost and high efficiency, since power electronic converter designed and leading and the sophisticated appropriate control technique. And this particular slide, we can see these are the power factor controller performance. Here the few advantages that is also shown, like easy functional and safety spacing, isolations and regulation stretch, and across the power factor choke, and there is a small difference to input to output voltage. Hence, Merit uses smaller value of inductor comparatively, and these ease of control, no need to AC line sense. And similarly, it has also some certain limitations, and what the limitations, the inherent AC line current crossover distortions restricts for achievable total harmonic distortion and power factor. And based use on the configurations, it is required to use either a high side bus voltage sense or a high side drive switch, and complicated surge management, since there is no direct link, and due to lower output voltage, hence a large bulk power capacitor is required with a lower hold of time, and it requires a voltage loops with the lower bandwidths, and with the slower transient response due to the higher percentage of bus voltage ripple in comparison to the case of a boost converter. This by like incorporating the active power factor converters in DPS in all mentioned prefer can be achieved, and the research still in progress to accomplish a better efficiency and fast dynamic response and high power inclinations with the stiff regulatory standards that inspires to improve performance of the active power factor converters are for DPs with some control technique and simple elongated PWM technique are integrated in this particular work, and hence and for this improvement of power factor and TSD during the step change in load current and line voltage to this work has to be shown for the coming some slide. And these slides where we have seen the control schemes for our power factor controller for a boost converter. You see these circuit diagrams. There are a variety of control methods, among which any one method can be used for power factor controller application. In general,
Hello,
for any
hello, sir.
hello
Your
hello
slide is not moving. Actually, you are in fourth slide.
it's moving.
No,
It's
now
moving?
it is moving. Now it is moving, but
Now
before it
now
was
it's
stuck in fourth only.
Now I am just telling control scheme for power factor boost converter. Is it visible?
Yes, it is visible.
Sorry, sir, because here I can see in my laptop it is moving, but there it is simply stuck on. Anyhow, I'm just changing. Now I'm just going to tell about this control scheme for power factor boost converter. Is it visible, sir? Okay. So you can see this circuit diagram. A voltage feedback compensating loop is used as the outer loop to keep the bus voltage to a fixed DC in a predefined reference value. In inner loop known as the current loop, which has to be controlled to the inductor current to a specific level, and to set the inductor current with the aim to be as like as possible to the rectifier input or DC voltage, keeping almost unity power factor. And this power factor supplies with the control loops implementations employed to achieve a stable systems with a tolerable dynamic behavior irrespective of the system loading conditions, which can be shown from this diagram. Here also you can see this is a power factor control strategy, which is characterized for our active this active control method, autonomous control line, and for CCM active control method is used, whereas automatic controller method is related to the DCM operations of the converter, and several control methods are under the active control methods, which is also shown few research work. Here, what are these? That one is a peak current control method. First one. The second one is like average current control method, and third one charge control method, hysteresis mode control, and borderline control, nonlinear carrier control, and discontinuous current PWM control. Now let us discuss with like peak current control method. What is that? What is that method? Peak current control method. It is the switch which can turn on the constant frequency, and it can turn off uphill inductor current reaches a level set up by the outer loop. Therefore, instant overcurrent switch protection is very easier, but there is a very noise sensitive control, and a compensating ramp is always required to add when this duty cycle exceeds 0.5. Otherwise, the control is inherently unstable, and that was reported in a research paper. And the switch now, and the switch is getting tuned on with a fixed frequency by a clock signal, as shown in the figure. You can see the figure 2, which is mentioned, and it is turned off when the sum of the positive ramp of the inductor current, so that is nothing but the switch current, and external ramp, that is compensating ramp, touches the sinusoidal current, which is reference as shown in figure 2. Usually this reference can be attained by multiplying a scaled replica and rectified voltage V0. Rectified voltage, this rectified voltage V0 is V0 is the times with the output voltage voltage to scaled a error amplifier, and which sets the current reference amplifier for a natural synchronization of the reference. Okay, so let us come to the next slides. Sorry. So this particular slide where we can see this is a sliding mode control schemes. Here the for boost converter. See this circuit diagrams here is implemented for the power factor boost converter, and this figure in represent the basic circuit diagram for power factor controller boost converter, which is governed by the sliding mode or sliding mode controller. Okay. Now look this one. See now, let me just this control method is a better improved input current waveform, and a current error amplifiers is in the figure, which can filter the inductor current which is sensed earlier, and the output of the current error amplifier which drives a PWM modular, and this inner current loop tends to reduce the error between the average input current IG and it's a reference, and the latter is obtained by a peak current control. Okay, and some considerations can be also realized with respect to this these control schemes, where we can see that particularly which this method like overpowers the complications of the peak current control method by introducing a high gain integrating current error amplifier CA, which is in the current loop. Now if we try to use this sliding mode control scheme for power factor control for boost converter, so what is the advantage for those ones? So few advantages also used to get while designing this for sliding mode control for scheme for power factor control for boost converter. The first one is like it's a fixed switching frequency. The no need to external complications. Then less it is very less sensitive to the communications compensating ramp, and less sensitive to the communications noises and due to the current filtering, and better input current wave from the peak control method, and it's very low crossing of the line voltage due to the due to that is very close to 1. And if you disadvantage there, like here, inductor current must be changed, and which cannot be measured very easily. And a current error amplifier is disable, and it is we take into account of by different converter operating point during this life cycles. So this slides you have seen the mathematical few expressions where we have systems I try to get out of these things. So like boost perfector converter this PI control strategy is the control variables that is X is the error and X2 is the voltage, and with the initial or high which is the on regulations for both the output voltage and inductor current. Hence the follow their reference precisely X1 which is given this formula X2 and X3. The switching functions so by U of I, and the for sliding mode operations, 3 necessary conditions which has to be the heating, existence, and stability conditions, resulting the control function and heating in conditions. So you can see this particular the strategies where we have to check these conditions has to be satisfied, and while coming to designing this the controlling method. Now coming to the see another this mathematical expression for modeling. Also here also we have also seen this here also the continuous conduction of power factor boost converter, and it's a time differentiations like from equations 2 we got this system dynamic model x1 dash and x2 dash and x3 dash we have done in that way. So we have seen where u dash is equal to 1 minus u 1 minus u, and it is considered as the investor logic of u. So this is the mathematical expression, so I'm not going to in depth here. And this is the also like where our the u equivalent this expression is defined by this ratio, and this controller which is driven and executed through a PWM comparing the u which is duty ratio of the PWM controller, and the control law equations is described in figure. And this boost converter now always needs to be extensive operating conditions and the fast response, which is satisfactorily impossible by conventional PWM current mode controller. And this nonlinear controller offer a control of backing in this regards in comparisons with the conventional current mode controller. The nonlinear controller is able to provide a comparable fast dynamic response and inherent robust features with fixed operating frequency and stable for large operating range, and least deviations for settling time over wide operating range, and low overshoots voltage relatively over wide angle. And this now coming back to because let me tell you about a few things here. So for dynamic evaluations control method, no, this is a one more new approach, like where we can see that the boost DC converter are the controller implemented for the boost power factor controller technique, and this control method advances the non-linearity and time varying properties of the system, and hence a superior control method, and some major limitations of this linear control method are overcome by this method, since it is the use of dynamic equations model which was explained by the last two slides. And feedback control needs an operation that in the existence of disturbances, the difference between the output of the system and the reference must tend to 0. And the key principle of the dynamic evolutions control techniques, the error state and the difference between the output systems and reference input must be reduced to 0 without loss of generally. The elementary idea is the minimization of state error by driving the state error to flow the definite track, and which ensure the null conditions of error state in increase on time. The target of the controller is to monitor characteristics of the system to work on governing and y0, and the evolutions track can be function of a linear path or exponential path, which was shown in the figure 4. And for the boost, the linear evolution path is chosen for the this controller schemes. Now coming to our the next for non-fragile observer-based sliding mode control for non-isolated onboard battery charger. So you can see from the slide that non-isolated two-switch buck boost converter topology is identified as the suitable topology for OBCs in terms of the low component counts, the number of switch, diodes, inductor, capacitor, with the significant efficiency we can achieve at 96, and a wide output range of converter operations. And it can behave as a buck and boost converter. In advantage, we can say the buck boost converter or power factor controller can be obtained. It is observed that non-fragile controller can provide the acceptable performance against the variation in controller gains during the implementations, along with the variation of the system parameter. And the observers and the mirror of the practical systems OBC, sometimes measurement of all the physical variables, voltage, current, and time derivatives voltage currents are difficult due to the presence of high frequency switching noise, a requirement of costly sensors of nonlinear ability of suitable sensors. Using observer after the measurement of one physical variable, remaining physical variable can be obtained, and therefore the development of non-fragile observer-based controller is necessary to overcome the challenges faced by existing controller of OBC. And the leading aim is to formulate a control law like which ensures of zero positions of state error, which function of the boost perfecter are non-fragile observer, where we can see that for DC converter, this controls signifies the duty cycles, and that has to be derived and modeling as per these things. And these connected now recommend simplifications and the linearizations of systems. Sorry, all the four terms of the control law, all terms of like this. The first one is coming from the feed forward term, and the second term is the represent the promotionals. And by using this duty cycle, we can achieve those equations. And this is the converter operations and modeling. So this particular slide where we have seen, and that's operating models for non-linear isolated OBC, that mode way, and that these waveforms also shown that rectify input voltage and the output voltage. And this technically, actually, this controller has a time varying state feedback, a discontinuous control law due to which switching from one continuous structure to another according to the existing situation of the state variable in the state space, which is possibly with high frequency. And the objective is to enforce the dynamics of the system under control flow and desired and predetermined. And sliding module, a controller technique is implemented for a power factor controller boost converter, which represent the basic circuit diagram of power factor controller boost converter governed by a sliding mode controller. And these control schemes and power factor and this power factor controller, sliding mode controller, and this control schemes for power factor boost converter is begin with the selection of sliding surface, uh, sliding surface, and this boost converter governed by a sliding factor boost converter begins with the selection of sliding in current makes the direct surface and the difference of V0 V reference just now I told, and by using this to cascade control loop now achieve from the voltage error and the output voltage loop produce the reference current, and the stability criteria and existence of the sliding mode can be achieved by controlling the output voltage which is AC to DC converter, and the inductor current is controlled or by the inner current. Inner current makes the difference, and here these you can see this modeling of the converter where the small signal mode converter obtained by the state space averaging method, which is used to design the controllers. Let me come, and this this switching function is the logic state of the power switch S, which is defined as U. From SM sliding mode operation, these three necessary conditions, namely hitting, we have just gone through these equations here. No, sorry, just a second. See now. These factors are the introduced purposefully to down the scale equations and practical level of magnitude to make the duty ratio of the output controller always below 1 and multiplier. And the selection of the appropriate switching functions gives the satisfied heating condition, and to attain this existence from limit S is less than G, which is essential, and this can be obtained from the equations. The control law and the sliding gain coefficient should be designed in such a way to that it fulfill to the stability condition, and this is also make to sure that a trajectory is directed by the desired sliding manifold always towards to the stable operations. The result is not showing in this particular slide, but we have the input current waveform and that fundamentals, the frequency along with that magnitude of fundamental. Also we got sliding mode controller, boost power factor, input current, and total harmonic distortion that can be also tabulated, and from where we can easily understand those parameters. Now the linear. Now, what is the role for power factor in EV charges? So, role of electric vehicle charges is so these are these particular slides. So these are the equations. I'm not going in depth. So these equations, this theorem 1 and this theorem 2, it is there. So let us come to this here. In general, like. And now, what is the actually? Let us come to the topic. So, the power factor control for EV charges. Now, the main question is the power factor are in EV charges. So, it's the role of EV charge. Role of EV charge so is nothing but converting AC, like alternating current from the grid to DC direct current required by the EV batteries, and power quality challenges. There is also very important aspects for power factor in electric vehicle chargers. So chargers draw nonlinear loads and causing harmonics and distortion, that what we have explained. And low power factor leads to increased energy losses, which is reduced to the grid capacity, and penalties from the utilities, what is also explained. And to maintain a high power factor close to the unity while charging electric vehicles to ensure efficient energy transfer and grid stability. And those power factor control methods also we have studied, but in summary, if we try to see the passive power factor controllers, which utilize the passive components like capacitor, inductor, and transformers, and the advantage also we have seen it's a simple and cost effective. Limitations also we have seen it's a bulky, less efficient, and high power charges. Active power factor corrections, where we use the active electronic circuits or the boost converters by converters dynamically adjust the input current, which is matched with the voltage waveform. And advantage also we have seen that high efficiency and concept of lightweight and effective of a high power consumptions, and how to implement those EV chargers. So either we can go for the front end rectifier design, and most of the charging chargers, which include a front end rectifier with power factor circuitry, which is a onboard circuitry. And like if you try to give an example, like a boost converter, or this I'm not going to just telling all this what you call mathematical lesson. Now coming to the like implementations for EV chargers, that control technique we have discussed, and standard and compliances. Like EV chargers must meet the internationally power quality standard, like IEC 61003 3/2, and limits, which is harmonic contents, and IEEE 519, which is guidelines the voltage and current harmonics. And what are the benefit we can get for this perfecter controller, which can reduce the energy losses, improve grid stability, efficiency, and avoids penalties from utility companies, and enhance the lifetime of electrical components. And a practical example, if we try to see practical examples where if we try to consider a 22 kilowatt EV charger without power factor control, without power factor, let us see power factor 7, and it is come 31.4 or kVA. But when the power factor is going to be corrected and power factor becomes 0.7 to 0.9, if you try to calculate that apparent power, will come 22. The apparent power reduced, and which the maximum important thing is which reduce the stress on the grid and better utilizations of the available power. Now, what are the challenges we can face for the future trends? So challenges is nothing but the first challenge what we expect is a higher cost and advanced power factor circuits, and the design is complexity in design for bidirectional chargers. And future trend, if you go for the through research area, what we're going, so like integrations of AI and control, and widespread use of the solid state transformers for enhanced performance, and the changes of bidirectional power factor controller for vehicle. So in summary, you can say like power factor control is essential for ensuring the leveling of the advanced technologies with safe with the future electric vehicle charging systems. And this we can see like how the power factor is trying to control for EV chargers. We have just shown a very simplified way to like how the power factor is going to be controlled for EV charger, where we have discussed like basic with like introduction of power systems for power factor, how the power factor for EV charging system is happened, then power factor control media, and the implementation of electric vehicle chargers. And now if we go for the like conclusions, the line current harmonics minimization is essential to comply with the standard, resulting in increase in degree utilization of the grid power. So this was discussed from the initially for power factor corrections in general. And power factor controller is a technique which is undesirable effects of electrical loads that create and there are the number of techniques, there are the number of techniques for power factor based on the selection of electrical element, which is the passive power factor controller circuit use low frequency filter components to reduce harmonics. And moreover, in this technique, what we discuss, a power factor cannot be highly improved, and output voltage voltage is not controllable. And active switches, which is used in association with the element for active power factor controller approach and for the improvement of the line current shape and to obtain controllable output voltage. And for this DC to DC convert is employed and is operated at a high frequency shape. The line current wave from the sinusoidal is possible. And in summary, also we can say, like in active power factor approach, the boost power factor converter is taken since it is significant advantage as discussed in the earlier slides with suitable switching control strategy. And there are a variety of control method among with any one of the method which can be used as power factor applications in general for any control strategy of a voltage feedback compensating loop is used as the outer loop to keep the bus voltage or fixed predefined reference, and inner loop known as the current loop. And the power factor controller power supplies with the control loops implemented is employed to achieve a stable systems with a tolerable dynamic behavior irrespective of the systems, and which is employed and using this some conventional control technique and the methodologies we have shown on these things. So future future for trending work we can see for this type of buck boost power factor converter with the different controller that can be realized with the help of the MATLAB or simulations also, and which can be analyzed in real-time simulator for the considerations of the practical applications. And also the hardware implementations can be realized practically with the suitable control technique, and the switching loss can be considered, and suitable soft switching techniques can be introduced, and some special suitable optimizations which can be employed to ensure very high dynamic stability and very wide stable operation range. So that's all from my side for power factor controller for EV charges. Thank you, organizers.